Okay, cool. Yeah. Okay, so today, just give me a quick second to make sure that yeah. So today we'll be continuing discussion of CNN, stochastic gradient descent, and give a brief introduction to TensorFlow. I won't really go too much into it. Figure it's much more fun to really step into code of TensorFlow instead of you know I like to I like to leave it fun to you guys. Okay, so continue from last webinar. So one of the key property of stochastic gradient descent, there are a few things that few criteria that needs to be met. I think it actually is pretty intuitive, but you do have to. It makes sense to think about this now and then. So these are two properties. The error function needs to be differentiable, and it also should be continuous. So for you to go down the mountain or the curve, it you know you need to have a way to differentiate it, and there can't be bumps, because if there are bumps and you start making gradual changes and nothing changes, then you won't be able to derive. You won't be able to slowly go to the bottom of the valley there. It won't work. So from the previous notebook, remember the error is set to y hat minus so this essentially is prediction, and this is the y and y hat. That's the error. So you can tell that this is both differentiable and continuous right here. If you change as you change y hat, it actually gradually changes. Doesn't There's no jumps anywhere. This is a linear function, and it it is I mean, of course, with respect to y hat, it is differentiable. Let me just make it go. So with the previous example, you also noticed how hard it was to for the multi no for the perceptron to use stochastic gradient descent to um, arrive at the correct well, actually optimal classification. There's two reasons. One was because the x variable was very large in size. The second was actually is because that the result is not continuous, and therefore it's you either are I think in a way that you are either completely wrong. The prediction is either completely wrong, if it's one where it should be zero, or zero should be where it should have been one, or that it is correct and now it just no longer it doesn't do what it doesn't make any changes for you once it classifies it correctly. Um, this was there was actually a section in the lessons that mentioned something similar to this for perceptrons. Essentially, the difference between perceptrons, so the stochastic gradient descent using regression is that for stochastic gradient descent with regression, it will still so say you have let's say this sum here or whatever this is. This was let's say 0.6, right? Of course, this is not done in the same way. Like this is done if it's larger than 0, it classifies 1, or like the other way is classified as 0. But say you change this to use a different equation, say 1. If it's greater than 0.5, then it's 1, and else it is 0, right? So let's say greater than 0.5 means this is well, this is really makeshift. Here, right? In this case, right, if you have 0.6, it's not and, it's not going to do anything. Unless the reason is that if you see, you know what, let's see, right, and y1 it's not going to do anything. This is because we was the predict applied it to 1, right? Actually, no, actually, this is well, you get the picture. This is well, let me just explain this. You can see which so nothing to do. Whereas still away from 1, right? So it still keeps going. In the slide or in the lesson, it says SGD will keep getting this to be closer to the result, which should classify as 1. But if you have a perceptron and you use a kind of step function to classify it, then it won't do it. Anything like that. So one of the way to go around this is instead of using as kind of a step function to do the prediction, you can use a continuous function like sigmoid. Okay, this will be the score in here would have been this result here. This is essentially the linear activation result. Result of everything into it. So and one of the exercises that you so how can I see softmax is the same as sigmoid function for two output for two classes, right? So one of the derivation way to derive that is I say right, this would this essentially is saying the for softmax. The equation for softmax is like this, right? And we can do it for um, y equals 1, and it result in something like this. And of course, you can do factorization, to reduce it to this format, look like this, okay? And then you factor out the negative, and this, you can see that this essentially is a score right here, and this function is the same as sigmoid here. Right? And of course, there's more detail they can find from here. From the stats exchange. Okay, so there's also a section on cross entropy. I'm just going to go through how cross entropy will have been applied in your code. So suppose you have labels like this. This is your label, right? 0, 1, 0, and your model prediction is like this. This will give you a very high log loss. Okay. This is an example of multi-class cross entropy. So your cross entropy will be defined as for for the the label and your predictions from labels and y hat, your predictions. Right? Each one of them will have two parts. One part is like it's 1 minus the label times log and of 1 minus p, which are prediction. Another part is y times log of p. Right. So you can see no, this is just saying like you can see that this there is a very large log loss because the prediction were wrong. Right. The first portion collects errors for false negatives. So if you're supposed to predict a 1 for the class, so the label is a dog, and the prediction say there was a very low probability of the data set being a dog. It predicts it's not a dog, then this will be very high error because the prediction will be a very low value, and the log of a very small value will be a very large. Will be quite large, and then you have 1, which is supposed to be positive. You find that this part will collect um, false negative, so it wasn't negative, but it believes that it was negative. The second part is there to collect error for false positives, right? So if if your prediction strongly believes something that is not positive, so 1 minus 0 would be 1, and this would be some large number because you have predicted it to be close to 1. So it would never actually be 1, but you predicted it close to be 1, and it's not, and you times the log, then you have some large number here. And if we run this, it'll get a very large log loss, and we fix this to be more correct. You can see the log loss is being reduced here. So this is that reduce the false negative, and let's reduce the false positive. So, yeah, you can see the log loss become even smaller. So let's put together stochastic gradient descent and back propagation. This code is borrowed from machine learning master. You couldn't find the uh, machine learning from scratch portion of it, but anyways, you can find if you're interested in learning more from the series, you can find that portion on the site itself. Right, so from let's just setup part here. Initialize a network. So this is just initializing random weights. You can see that we have two hidden layers here. Prediction. This is a feed forward activation. So this is essentially the linear activation here. This is the sigmoid. Um, so it takes the linear activation and or the result of your neuron in this case, um, and apply activation here, right? And this is the forward propagation step, and that's a derivative of sigmoid function. Backward propagation errors, propagate the errors backwards, and update weights, and this is the training the network. All right, so let's go through this. We're gonna train the network, right? See, for every epoch, you take each row, you first forward propagate it to get the output, which is your predictions, and so of course now you compare those predictions against what was expected, right? This part you collect the errors, error sum here. Like row -1. Okay, and you back propagate the error, and then you update the weights, right? So back propagation. Let's look at back. I thought the back propagation here. So actually, this error is just being reported. This is actually not being used anywhere. The actual error is um, being kept tracked here. Okay. So this is for the input layer. Actually, let me see. No, actually, this is the input layer. So if you have the input layer, which is essentially saying from here, you can see that this is saying that the last layer, or yeah, it's kind of upside down. So this is the input layer. You're collecting the error on the input layer, and then for each one of these, you get um, the delta, which is essentially hold on. Actually, no, you get the delta from here. If it's the input layer, you append it to the error. Otherwise, you take the error and you multiply that with the delta, because the delta was the last layer's error and error rate. And that is the rate of change. delta. Actually, no. This is where you get the delta because that's a derivative derivative function of the sigmoid, which is your activation. That you set up delta here. If you are the last, if you are the sorry, I thought this was a loop. If you are the input, this is input layer. Start setting up the errors. Otherwise, you start setting the errors to be the weight times the delta, which was previous errors, and the delta. Let me derive this, the error and the derivative rate of change here. Yeah, and you can do a quick run here. So this is this is more or less a contrived data set, and these go from 0 and 1s, and there's the predictions here, and actually it prints out the look of the network structure of the network, and you can see actually that's pretty close. Well, actually, this is multi-layer perceptron. Um, Actually, this perceptron, by the way, is not let's see. Yeah, this perceptron is not the same as the previous one. This one is actually using regression instead of where like this one. It's a step function. This one is actually using sigmoid, and the trains much better. You can see why this gets very good results. Um, so so I'm gonna okay. So this actually has the code above demonstrate how the below structure is implemented for forward propagation. So you have weights. You have two different different neurons. So this is one neuron. This actually no. This is one layer. This is the other layer, right? And there are weights applied to it, and then you apply a sigmoid to that those different those layers, and you stack them, and it comes out like this. There's um, this article or this article briefly explain why ReLU is a preferred activation function choice for deep convolutional neural networks. One of the reason is that this sigmoid, it is a very dense activation because every it's going to try to activate uh, every neuron, but it's yeah, image. You can imagine that not not every pixel in the image is significant, and there are a lot of them, and you want a sparse activation, and that's why you would use ReLU. There's also reasons why there is a alternative called the leaky ReLU. This is because of the flat part on the ReLU where it can cause certain neurons to become permanently dead. And the leaky ReLU actually is there to allow it to recover from being dead. But yeah, that's the gist of it. So this is There's just some quick mentions here. Because I believe you guys have TensorFlow in your workspace, and you don't really have to reinstall it. If you do try to reinstall it on Windows, it is going to be tricky. You will need Python 3.6.5, I believe, for the older version of TensorFlow, not 2.0. 2.0 is it's quite different. I have not tried it, so this is a simple example about this TensorFlow for Hello World. You can actually see that, wow, that's fast. Because I had it running, but if you just run it for the first time and you're not on GPU, it will take some time. Okay. And here's something I'd like to mention just for TensorFlow, is that you actually can do something like that. That's actually something you can't really do in PyTorch. So referring to a tensor, and I can say I can do this, right? This is fine, but in PyTorch you do this, it's not going to work. You can't compare a tensor in PyTorch to or whatever tensor structure in PyTorch um, to none. Something like it's really weird. I see a lot of people doing try catch. I'm not sure if that's the only way to do it, but you can do things like this in TensorFlow and retain just very clear logic still, which I thought was nice about it. Even though it like I know TensorFlow is not the most intuitive compared to things like Keras and PyTorch. So brief about batches, momentums, and learning rate decay. Because computing loss based on like all the data is kind of expensive. We do stochastic gradient descent. All the examples that was implemented in code here are one batch. They're based on batches of one, but if you don't specify batch, it's gonna use all the data, and that is very it's very time consuming. Um, so what one way to have efficient calculation is to use a sample instead. So this sample is known as a batch. So for example, batch of 10, it takes 10 out of like your thousands of samples. I believe a recommendation from watching Lex, the one interview Lex did with, I forgot who it was, but he recommended batches no larger than 60. Momentum is a technique where you take the running average of the loss instead of the current batch current batch loss. So actually, hold on, let me see. Learning rate decay. Actually, this is a technique where learning rate is slowly reduced throughout the training. Um, just because you don't at the start there is probably a lot of errors and you want to use high learning rate, but as you get to the closer to the chasm, you want to use a slower learning rate, so it doesn't jump. So it doesn't jump around as much. The reason being is that you can see the gradient slowly vanishing towards the bottom of the bell, so it makes sense to descend much slower. Thinking intuitively like that. Um, yeah, I think that's all for today. Um, yeah, see you next time. Thanks for tuning in.